Good evening, everyone, and welcome to Midnight Knowledge. Tonight, we're going to learn about inventions that vanished. As you settle in, please take a moment to let us know where you're listening from, and feel free to subscribe. Now, take a moment for some deep breaths, letting your mind and body relax for a good night of sleep. Before we begin tonight's lesson, I have a question for you. How many of you checked your smartphones this evening? Right, almost everyone. Now, how many of you know how to make concrete that can self-heal underwater and last for 2,000 years? Ah, I see we have a knowledge gap here. What a shock. So let's fix that. Welcome to what I like to call history's greatest oops moments, or as your syllabus more formally states, lost knowledge. Forgotten inventions that vanished. Tonight we're going to explore some of humanity's most remarkable achievements that somehow managed to slip through the cracks of history like loose change in a couch cushion, except infinitely more valuable and considerably harder to find with a flashlight. The nature of lost knowledge. Before we dive into specific examples, let's establish what we mean by lost knowledge. We're not talking about your grandmother's secret cookie recipe that she took to her grave, though I'm sure that was tragic in its own right. We're discussing sophisticated technologies, scientific understanding, and technical processes that were once well established, but gradually disappeared from human knowledge, sometimes for centuries. This phenomenon occurs for various reasons. Sometimes it's catastrophic. Libraries burn, civilizations collapse, and knowledge dies with its practitioners. Other times, it's more mundane but equally devastating. Economic factors make certain practices unprofitable. Newer technologies replace older ones so completely that the original knowledge atrophies, or political upheaval disrupts the transmission of specialized knowledge from master to apprentice. Think of it this way. If you suddenly had to explain to an alien how to make a pencil from scratch, and I mean from mining the graphite to harvesting the wood to creating the metal ferrule, could you do it? Most of us couldn't, despite pencils being one of our most basic tools. Now imagine that happening to entire civilizations with far more complex technologies. Roman concrete, the recipe that built an empire and then vanished. Let's start with one of history's most frustrating losses, Roman concrete. Now, I know what you're thinking. Professor, concrete is concrete. You mix cement with water and aggregate, and boom, you've got something that hardens into rock. Well, hold on to that thought, because Roman concrete was to modern concrete what a smartphone is to two tin cans connected by string. Roman concrete, or opus caementicium as they called it, was first developed around the 3rd century BCE, and it was nothing short of miraculous. While our modern concrete begins to deteriorate after decades and requires constant maintenance, Roman concrete structures have been standing for over 2 millennia. The Pantheon in Rome, built around 128 CE, still has the world's largest unreinforced concrete dome, and it's in remarkable condition. Meanwhile, highways built in the 1950s are crumbling faster than cookies in milk. But here's where it gets really impressive. Roman concrete actually gets stronger underwater over time. Modern marine concrete degrades rapidly in seawater, which is why maintaining harbors, bridges, and offshore structures costs billions annually. Roman harbors and piers, submerged for centuries, remain structurally sound and continue to strengthen. The Romans achieved this through a combination of volcanic ash from specific regions around Naples, particularly from Pozzuoli, which gave us the term pozzolane, limestone, seawater, and what can only be described as chemical wizardry. When seawater interacted with the volcanic ash in their concrete, it created a chemical reaction that produced tobermerite, a mineral that actually strengthens the concrete matrix over time. Recent studies using electron microscopy and X-ray microtomography have revealed that Roman concrete contains rare crystalline structures that form when the lime clasts in the mixture react with seawater over extended periods. These crystals act like a self-healing mechanism. When cracks form, they provide pathways for further chemical reactions that fill the cracks with new binding minerals. So, why did we lose this technology? The fall of the Roman Empire certainly played a role, but it wasn't immediate. The knowledge persisted in the Byzantine Empire for several more centuries. However, the specific volcanic materials were geographically limited, and as trade networks collapsed and territorial control shifted, access to these materials became restricted. Additionally, the craftsmanship was highly specialized. It required not just knowing the recipe, but understanding how different volcanic ashes from different regions behaved, how local climate affected curing, and countless other variables that were passed down through generations of practitioners. By the medieval period, builders were using lime mortar and later, simpler cement formulations that were easier to produce locally but far less durable. When the modern Portland cement was developed in the 19th century, it was revolutionary for its time but still inferior to Roman concrete in terms of longevity and environmental resistance. Today, researchers are frantically trying to reverse engineer Roman concrete, not just out of historical curiosity, but because it could revolutionize modern construction and dramatically reduce the environmental impact of cement production, which currently accounts for about 8% of global CO2 emissions. Greek fire, the medieval weapon of mass destruction. Moving from construction to destruction, let's discuss Greek fire, perhaps history's most jealously guarded military secret, and one that was kept so secret that it was eventually lost entirely. If Roman concrete was about building things to last forever, Greek fire was about making sure your enemy's things didn't last until tomorrow. Greek fire was developed by the Byzantine Empire around 672 CE, most likely by a Syrian refugee named Kallinikos of Heliopolis. This incendiary weapon was the nuclear deterrent of its day. A liquid that burned on water, couldn't be extinguished by conventional means, and could turn the tide of naval battles single-handedly. The Byzantines used Greek fire primarily in naval warfare, projecting it through bronze tubes mounted on their ships, essentially creating medieval flamethrowers. The psychological effect was as devastating as the physical damage. Imagine being an enemy sailor watching your wooden ship catch fire with flames that water couldn't put out. Arab sources from the period describe it as liquid fire and recount how it struck terror into the hearts of experienced warriors. The secret was so closely guarded that knowledge was restricted to the imperial family and a handful of trusted craftsmen. The formula was passed down through generations like the world's deadliest family recipe. Manufacturing was centralized in Constantinople, and the ingredients were compartmentalized. Different people handled different components, so no single person except the master craftsman knew the complete process. This paranoid secrecy worked remarkably well for about 400 years. Greek fire helped the Byzantines repel Arab sieges of Constantinople in 674 to 678 and again in 717, thought 718. It remained a decisive Byzantine advantage in naval warfare throughout the early medieval period. However, this very secrecy ultimately led to its loss. When the Byzantine Empire began its long decline, the infrastructure supporting Greek fire production crumbled. The specialized craftsmen died without properly training successors. The supply chains for rare ingredients were disrupted, and political instability made it difficult to maintain the extreme security measures necessary to preserve the secret. By the time of the Fourth Crusade in 1204, when Constantinople was sacked, the secret of Greek fire had already been lost. The Crusaders found the equipment but not the knowledge to use it. Later attempts by various groups to recreate Greek fire were largely unsuccessful. Modern historians and chemists have proposed numerous theories about its composition. The most likely candidates include combinations of petroleum, pine resin, sulfur, lime, and various other chemicals. Some theories suggest it might have included saltpeter, potassium nitrate, or even primitive forms of napalm-like substances. However, without definitive historical records, we may never know the exact formula. The loss of Greek fire demonstrates how political paranoia, while effective for maintaining short-term military advantage, can be catastrophic for long-term knowledge preservation. The Byzantines were so afraid of their enemies learning their secret that they prevented themselves from learning it too. Damascus steel, the blade that cut through history. Let's move from chemical warfare to metallurgy with Damascus steel, a technology so advanced that modern scientists are still trying to figure out exactly how it worked. If you've ever seen a genuine piece of Damascus steel, you'll understand why medieval warriors would pay fortunes for these blades and why they became the stuff of legend. True Damascus steel, also known as Wootz steel, was produced primarily in India and Sri Lanka from around 300 BCE to 1700 CE. The steel ingots were then shipped to Damascus and other Middle Eastern cities, where master smiths forged them into weapons and tools. The resulting blades were renowned for their distinctive watered pattern, incredible sharpness, and legendary durability. European crusaders encountered these blades during the medieval period and were astounded by their quality. Damascus steel could reportedly cut through European swords, slice falling silk scarves in half, and maintain their edge through extended combat. The blades were so sharp they could cut through a hair dropped onto the blade, and so flexible they could be bent into a complete circle without breaking. But what made Damascus steel so special? Recent metallurgical analysis has revealed that these blades contained carbon nanotubes and nanowires, structures that materials scientists didn't intentionally create until the late 20th century. The steel also contained carbide bands that created the distinctive watered pattern and contributed to the blade's exceptional properties. The production process was extraordinarily complex and took advantage of very specific ore compositions found in particular regions of India and Sri Lanka. The iron ore contained just the right trace elements, including vanadium, chromium, manganese, and other compounds that contributed to the steel's unique properties. The forging process involved repeated heating, folding, and cooling cycles that could take months to complete. The knowledge was closely held by specialized craftsmen who passed their techniques down through family lines. However, several factors contributed to its loss. First, the specific ore sources began to be depleted by around 1700. The English East India Company's disruption of traditional trade networks also played a role. Additionally, the rise of firearms reduced demand for high-quality bladed weapons, making the expensive and time-intensive Damascus steel production economically unviable. The secret was essentially lost by the 18th century. Modern attempts to recreate true Damascus steel have had limited success. While contemporary smiths can create beautiful pattern-welded steel that resembles Damascus steel visually, reproducing the exact metallurgical properties of historical Wootz steel remains elusive. Some researchers believe they've come close using modern understanding of metallurgy, but without the original ore sources and the accumulated generations of craftsman knowledge, true Damascus steel remains one of history's lost technologies. Roman medicine, advanced surgery in togas. Now, let's discuss something that might surprise you. Roman medicine was far more advanced than most people realize, and some of their medical knowledge wouldn't be rediscovered in Europe until the Renaissance or later. While we often think of ancient medicine as primitive superstition mixed with bloodletting, Roman physicians were performing sophisticated surgeries and using medical techniques that would make a modern doctor nod in approval. Roman military medicine in particular was remarkably advanced. Army surgeons could perform cataract surgery, remove bladder stones, perform complex bone surgeries, and even conduct primitive forms of brain surgery. They had an extensive pharmacopoeia of effective drugs, sophisticated surgical instruments that wouldn't look out of place in a modern operating room, and medical knowledge that was systematically documented and taught. Consider the surgical instruments found at Pompeii and other Roman sites. Bone forceps, surgical scissors, scalpels, probes, catheters, and even vaginal specula that are virtually identical to modern designs. Roman surgeons understood the importance of hygiene and sterilization. They boiled their instruments and used wine as an antiseptic. They performed successful operations to remove cataracts, repair hernias, and set complex bone fractures. Dioscorides, a Roman army surgeon in the 1st century CE, wrote De Materia Medica, a 5-volume work describing over 600 plants and their medical uses. This work remained the primary medical text in Europe for over 1,000 500 years. Galen, another Roman physician, made fundamental discoveries about anatomy and physiology that weren't improved upon until the Renaissance. Roman military hospitals were marvels of organization and medical care. They had specialized wards, trained nursing staff, clean water supplies, and systematic approaches to treating different types of wounds and diseases. The survival rates for Roman soldiers after surgery were remarkably high given the technology available. So what happened to all this medical knowledge? The collapse of the Roman Empire certainly played a role, but it was more complex than simple civilizational decline. The rise of Christianity brought different attitudes toward the body, disease, and medical intervention. Some early Christian leaders viewed illness as divine punishment or a test of faith, discouraging medical treatment in favor of prayer. Additionally, much Roman medical knowledge was preserved in Greek texts, and as knowledge of Greek declined in Western Europe, access to these texts diminished. The Islamic world preserved much of this knowledge and continued to advance medical science, but it took centuries for this preserved knowledge to filter back into European practice. The medieval period saw a general decline in surgical practice in Europe, partly due to religious prohibitions, and partly due to the loss of the systematic medical education that had characterized Roman practice. When European medicine finally began to advance again during the Renaissance, physicians had to rediscover many techniques that Roman doctors had routinely used 1,000 years earlier. The Antikythera mechanism, ancient computers. Let's shift gears dramatically and talk about the Antikythera mechanism, a device so advanced that when it was discovered in 1901, scientists literally couldn't believe what they were seeing. It's often called the world's first analog computer, and that's not hyperbole. The Antikythera mechanism dates to around 100 to 50 BCE and was discovered in a Roman shipwreck off the Greek island of Antikythera. When researchers first examined it, they found a corroded bronze device containing dozens of precisely engineered bronze gears, technology that wasn't supposed to exist until at least 1,000 years later. After more than a century of study using increasingly sophisticated analysis techniques, including X-ray tomography and 3D modeling, we now understand that this device was essentially an ancient astronomical calculator. It could predict the positions of the sun, moon, and planets, forecast solar and lunar eclipses, track the 4-year cycle of the Olympic Games, and calculate various astronomical phenomena with remarkable accuracy. The mechanism contained at least 37 bronze gears, possibly more that were lost to corrosion, arranged in a complex system that could perform calculations equivalent to those done by modern computers. The gear ratios were calculated to astronomical precision. For example, the lunar calendar gear system achieves accuracy to within 1 part in several million. But here's what's truly remarkable. The device incorporated knowledge of the elliptical orbit of the moon that wasn't officially discovered until Kepler's work in the early 17th century. The ancient Greeks, who built this mechanism, somehow understood that the moon's orbit was not perfectly circular and had built this knowledge into their mechanical calculator. The precision of the gear cutting and the sophistication of the mechanical engineering suggest that the Antikythera mechanism was not a unique device but rather represented a tradition of such instrument making. There are references in ancient texts to similar devices created by Archimedes and other mathematicians, suggesting that complex mechanical computation was more advanced in the ancient world than we previously believed. So why did this technology disappear? Several factors likely contributed. First, such devices were extremely expensive to produce and required master craftsmen with specialized knowledge of both astronomy and precision mechanics. The economic disruption following the collapse of the Hellenistic kingdoms probably made it difficult to maintain the specialized workshops necessary for such complex manufacturing. Additionally, the rise of different philosophical and religious traditions may have reduced interest in mechanical approaches to astronomical calculation. The knowledge was probably also closely held by small groups of specialists, making it vulnerable to disruption. The loss of this technology meant that complex mechanical calculation didn't reappear in Europe until the development of mechanical clocks in the medieval period, and even then, Devices of comparable computational sophistication weren't created until much later. Library of Alexandria, the great knowledge hub. Speaking of lost knowledge, we can't have this discussion without addressing the elephant in the room, or should I say, the library that's no longer in the room. The Library of Alexandria represents perhaps the greatest concentration of knowledge loss in human history, though the reality is more complex and gradual than the popular image of a single catastrophic fire. The Library of Alexandria was established around 295 BCE by Ptolemy I and was designed to be a universal library containing all human knowledge. The Ptolemaic rulers pursued this goal with remarkable dedication and resources. They required ships entering Alexandria's harbor to surrender any books or scrolls for copying. They borrowed official copies of great works from other cities, supposedly to copy them, but kept the originals and returned the copies. They sent agents throughout the Mediterranean world to acquire texts. At its height, the library may have contained between 400,000 and 700,000 scrolls, covering every field of knowledge known to the ancient world. It wasn't just a library, but a research institution, the world's first university, if you will. Scholars from across the Mediterranean came to study, conduct research, and teach. The institution produced groundbreaking work in mathematics, astronomy, medicine, geography, and numerous other fields. Eratosthenes calculated the circumference of the Earth with remarkable accuracy while working at the library. Euclid developed his geometric principles there. Hipparchus discovered the precession of the equinoxes. Aristarchus proposed that the Earth orbited the Sun, nearly 2,000 years before Copernicus. The list of intellectual achievements associated with the library is staggering. So, what happened to all this knowledge? Contrary to popular belief, there was no single moment when the library burned down and all knowledge was lost. Instead, the decline was gradual and resulted from multiple factors over several centuries. The library began declining in the Roman period due to reduced funding and political instability. Different religious and philosophical factions sometimes clashed, leading to destruction of texts deemed objectionable. The rise of Christianity brought different priorities, and some early Christian leaders viewed pagan learning with suspicion. The Arab conquest of Alexandria in 641 CE is often blamed for the library's final destruction, but by this time, the institution had already been in decline for centuries. Many texts had been lost, damaged, or transferred elsewhere. The Arabs actually preserved much Greek learning and continued to value scholarship. The real tragedy is not just what was lost, but what could have been. If the library had continued to function as a center of learning and research, human knowledge might have advanced by centuries. The scientific revolution, the Enlightenment, and modern technology might have occurred much earlier. We lost not just the knowledge that existed, but the intellectual momentum that might have carried human understanding much further. Chinese inventions that took centuries to reinvent. Let's take a moment to discuss the curious case of Chinese inventions that were lost to the Western world and had to be independently rediscovered centuries later. This isn't exactly lost knowledge in the traditional sense, but rather knowledge that existed in one part of the world while being unknown in another, sometimes for remarkably long periods. Take printing, for example. The Chinese developed woodblock printing around 600 CE and movable type printing around 1040 CE, about 400 years before Gutenberg. Chinese books were mass-produced using sophisticated printing techniques, while Europeans were still painstakingly copying manuscripts by hand. Yet this technology remained largely unknown in Europe until much later. Paper money is another example. The Chinese began using paper currency during the Tang dynasty for nearly 600 years before paper money appeared in Europe. They had sophisticated systems for preventing counterfeiting, government oversight of currency production, and economic theories about monetary policy that wouldn't be developed in Europe until much later. The magnetic compass was used for navigation in China by the 11th century, but didn't appear in European navigation until the late 12th century. Gunpowder was invented in China around 850 CE, but didn't reach Europe until the 13th century. The list goes on. mechanical clocks, seismographs, cast iron production, and numerous other technologies. Why did these knowledge transfers take so long? The Silk Road and other trade networks did facilitate some technology transfer, but communication across vast distances was slow and uncertain. More importantly, technologies often require not just knowledge of their existence, but understanding of the underlying principles, manufacturing techniques, and supporting infrastructure. Additionally, different civilizations had different priorities and values that affected which technologies they chose to adopt or develop. What seemed revolutionary in one context might seem less important in another. The irony is that many of these Chinese inventions were probably independently developed multiple times in different places before finally taking hold. Human ingenuity tends to converge on similar solutions to similar problems, given enough time and resources. The Mayan astronomical knowledge. The Maya developed one of the most sophisticated astronomical and mathematical systems in the ancient world, with knowledge that in some areas exceeded that of contemporary European civilizations. Their understanding of celestial mechanics, their calendar systems, and their mathematical concepts were remarkably advanced. Yet much of this knowledge was lost during the Spanish conquest and subsequent cultural suppression. Mayan astronomers could predict solar and lunar eclipses with remarkable accuracy, tracked the movements of Venus with precision that wasn't matched in Europe until much later, and developed a calendar system more accurate than the Julian calendar used in Europe at the time. They understood the concept of zero independently of Indian mathematicians, and developed sophisticated systems of mathematical notation. The Dresden Codex, one of the few surviving Mayan books, contains astronomical tables that demonstrate their ability to predict celestial events hundreds of years in advance. Their Venus tables, for example, show they understood that the morning star and evening star were the same planet and could predict its appearances with an error of only a few hours over centuries. Mayan architecture also demonstrates sophisticated understanding of astronomy. Buildings at sites like Chichen Itza and Caracol were precisely aligned with celestial events. The famous pyramid at Chichen Itza creates a shadow pattern resembling a serpent descending the staircase during the equinoxes, a feat that required precise mathematical calculation and architectural planning. The loss of Mayan knowledge was particularly tragic because it was systematic and deliberate. Spanish conquistadors and missionaries, viewing Mayan books as pagan and potentially dangerous, destroyed thousands of codices. Bishop Diego de Landa famously burned a large number of Mayan books in 1562, describing the event by saying, "We found a large number of books in these characters, and, as they contained nothing in which were not to be seen as superstition and lies of the devil, we burned them all." Only 4 Mayan codices survived this systematic destruction, and much of their astronomical and mathematical knowledge died with the literate class that maintained it. The irony is that European scholars were simultaneously struggling with calendar reform and astronomical calculation, problems the Maya had already solved. The printing revolution that almost wasn't. Here's a fascinating what-if scenario that demonstrates how easily knowledge can be lost or delayed. Around 1040 CE, a Chinese inventor named Bai Sheng developed movable type printing, individual characters that could be rearranged to print different texts. This was revolutionary technology that should have transformed Chinese society the way Gutenberg's press later transformed Europe. However, movable type printing in China faced several unique challenges. The Chinese writing system contains thousands of characters, making a complete set of movable type extremely expensive and cumbersome compared to the 26-letter Latin alphabet. Additionally, the Chinese already had efficient woodblock printing systems that worked well for their needs. As a result, movable type printing remained an interesting but impractical novelty in China for centuries. The technology existed but wasn't widely adopted. Meanwhile, woodblock printing continued to be the dominant method for producing books in China. When Gutenberg independently developed movable type printing around 1440, the Latin alphabet made the technology immediately practical and economically viable in Europe. The printing revolution began, transforming European society, education, and the spread of knowledge. But here's the fascinating part. If Chinese movable type printing had been more widely adopted and refined over the 400 years before Gutenberg, it might have spread along trade routes to Europe much earlier. The scientific revolution, the Renaissance, and the Reformation might have occurred centuries sooner. Alternatively, if the Chinese writing system had been alphabetic, the printing revolution might have begun in China around 1040, giving Chinese civilization a 400-year head start in mass communication and knowledge dissemination. This illustrates how technological adoption depends not just on invention, but on cultural, economic, and practical factors that determine whether new knowledge survives and spreads. Why knowledge gets lost, the systematic causes. Now that we've explored specific examples, let's examine the systematic reasons why knowledge gets lost. Understanding these patterns is crucial for preventing future losses and recognizing vulnerabilities in our current knowledge systems. First, there's the specialization trap. Many of these lost technologies required highly specialized knowledge that was concentrated among small groups of practitioners. When these communities were disrupted by war, disease, economic change, or political upheaval, their knowledge could disappear entirely. The more specialized and restricted the knowledge, the more vulnerable it became. Second, there's the oral tradition vulnerability. Much specialized knowledge was passed down through apprenticeship and hands-on training rather than written documentation. Master craftsmen taught their secrets to selected apprentices, but if this transmission chain was broken, the knowledge could disappear forever. Even when written records existed, they often assumed background knowledge that wasn't explicitly documented. Third, there's the economic obsolescence factor. Technologies that were once economically viable could become unprofitable due to changing circumstances, resource depletion, trade disruption, or competition from newer technologies. When there was no longer economic incentive to maintain specialized knowledge, it often atrophied quickly. Fourth, there's the political and religious suppression issue. Sometimes knowledge was deliberately destroyed or suppressed because it was associated with conquered peoples, rival religions, or politically dangerous ideas. The destruction of Mayan codices, the decline of classical learning in early medieval Europe, and similar instances show how knowledge can be lost through cultural conflict. Fifth, there's the infrastructure dependency problem. Many technologies required complex supporting infrastructure, specialized materials, particular geographical locations, established trade networks, or institutional frameworks. When this infrastructure collapsed, even well-documented technologies could become impossible to implement. Finally, there's what we might call the knowledge concentration risk. When knowledge becomes too centralized in particular institutions or locations, it becomes vulnerable to catastrophic loss. The Library of Alexandria is the classic example, but this pattern has repeated throughout history. Modern implications. What are we losing today? Before we conclude, let's consider what knowledge we might be losing today. In our digital age, it's tempting to think that knowledge loss is no longer possible. After all, we have the internet, digital archives, and unprecedented information storage capacity. However, we face new and sometimes more subtle forms of knowledge loss. Consider digital preservation challenges. Much of our current knowledge exists in digital formats that require specific hardware and software to access. How many of you can read a 5¼ inch floppy disk today? Digital files can become inaccessible surprisingly quickly as file formats become obsolete and software evolves. We're creating vast amounts of digital knowledge while simultaneously making older digital knowledge inaccessible. There's also the skill degradation issue. As automation and specialization increase, fewer people understand the underlying principles behind the technologies we use daily. How many people today could build a radio from basic components, or understand the fundamental principles behind internal combustion engines, or maintain complex machinery without computer diagnostics? We're becoming increasingly dependent on technologies that fewer and fewer people truly understand. Traditional craft knowledge is disappearing as industrialization replaces handmade production. Traditional building techniques, artisanal manufacturing processes, and specialized skills that took generations to develop are being lost as they become economically unviable. Even in academia, hyper-specialization means that knowledge in some areas becomes so narrowly focused that only a handful of experts worldwide fully understand particular subjects. When these experts retire or change fields, their knowledge can effectively vanish from human understanding. Lessons for knowledge preservation. So what can we learn from history's lost knowledge? Several principles emerge from our survey of vanished technologies and forgotten wisdom. First, diversity of preservation is crucial. Knowledge that exists in only one location, format, or tradition is vulnerable. The most resilient knowledge is that which is preserved in multiple forms, locations, and cultural contexts. Second, documentation must assume ignorance. Much knowledge was lost because the written records assumed background knowledge that wasn't explicitly stated. Effective knowledge preservation requires documenting not just what to do, but why it works, what can go wrong, and what assumptions underlie the process. Third, practical application preserves knowledge better than theoretical understanding alone. Technologies and skills that remain in active use are less likely to be lost than those that exist only in books or academic study. Fourth, institutional diversity protects knowledge. When knowledge preservation depends on single institutions or centralized systems, it becomes vulnerable to catastrophic loss. Distributed preservation across multiple independent institutions provides better security. Fifth, economic sustainability matters. Knowledge systems that depend on continuous economic support without generating value are vulnerable to changing economic conditions. Sustainable knowledge preservation requires finding ways to make knowledge valuable enough to maintain. Finally, cultural transmission is as important as formal education. Knowledge that becomes embedded in cultural practices and traditions often survives better than knowledge that exists only in formal educational systems. Conclusion: the ongoing challenge. As we conclude tonight's lecture, I want you to consider that we are both the beneficiaries of thousands of years of human knowledge accumulation and the potential victims of our own success. We have access to more information than any previous generation, yet we're simultaneously more dependent on complex systems that few people fully understand. The Romans, who mixed their miraculous concrete, probably never imagined that future civilizations would struggle to recreate their techniques. The craftsmen who forged Damascus steel likely assumed their skills would be passed down forever. The scholars at Alexandria couldn't have conceived that their vast collection of human knowledge would be scattered to the winds. Yet here we are, more than 2 millennia later, still trying to unlock their secrets. This should be both humbling and motivating. Humbling because it reminds us that our current technological achievements are not guaranteed to persist. Motivating because it shows us the incredible value of the knowledge we possess and the responsibility we have to preserve it effectively. The question for your generation is not whether you'll create new knowledge. You certainly will. The question is whether you'll also ensure that this knowledge survives for future generations to build upon. Because as we've seen tonight, the difference between temporary achievement and lasting civilization often comes down to how well we preserve and transmit what we've learned. Your homework assignment, and yes, there's always homework, is to identify one piece of specialized knowledge or skill that you think might be at risk of being lost today. Consider why it might be vulnerable, what would be lost if it disappeared, and what could be done to preserve it more effectively. Think like the historians of the future, who might be puzzling over our lost technologies and wondering how we could have been so careless with such valuable knowledge. Remember, today's cutting-edge technology is tomorrow's archaeological mystery. The question is, what are we doing today to make sure it doesn't have to be? And please, don't ask me to explain how to make Greek fire. If I knew that, I probably wouldn't be teaching. I'd be off somewhere becoming very wealthy, and possibly accidentally setting things on fire and putting them out because I'll be bored all day long. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you. Please make sure your phones are dimmed, as we're about to embark on a journey that will make your Instagram feed look positively mundane by comparison. Today we're discussing one of the most mind-bending possibilities in modern physics, the idea that black holes might not be cosmic vacuum cleaners of destruction, but rather gateways to, well, somewhere else entirely. Now, I know what some of you are thinking. Professor, did you accidentally pick up a Star Trek script instead of your lecture notes? I assure you, my notes are clearly labeled, though I admit the boundary between cutting-edge physics and science fiction has become remarkably thin these days. Before we dive into wormholes, extra dimensions, and the possibility that falling into a black hole might be less like meeting your doom and more like taking the universe's most extreme form of public transportation, let's establish our foundation. We need to understand what black holes actually are, how they work, and why some of the brightest minds in physics think they might be far stranger than we ever imagined. Part 1. Black Holes 101. More than just cosmic garbage disposals. What are black holes really? Let's start with the basics, because before we can discuss black holes as gateways, we need to understand what we're supposedly traveling through. A black hole is fundamentally a region of space-time where gravity has become so strong that nothing, not matter, not light, not even your regrets about skipping breakfast this morning, can escape once it crosses a certain boundary. This boundary is called the event horizon, and it's not a physical surface like the edge of a pool. Think of it more like a point of no return. Imagine you're in a canoe going down a river, and you reach a point where the current becomes so strong that no matter how hard you paddle upstream, you can't make progress back to where you came from. That's essentially what the event horizon represents, except instead of water current, we're dealing with the curvature of space-time itself. The mathematics behind black holes emerged from Einstein's general theory of relativity, published in 1915. Just months after Einstein published his field equations, a German physicist and astronomer named Karl Schwarzschild found an exact solution to these equations. Tragically, Schwarzschild died on the Russian front during World War I, shortly after making this discovery, but his solution, now called the Schwarzschild metric, became the mathematical foundation for our understanding of black holes. The Schwarzschild radius and event horizons. The Schwarzschild solution revealed something remarkable. For any object with mass, there exists a critical radius called the Schwarzschild radius. If you could compress that object down to fit within this radius, it would become a black hole. The Schwarzschild radius is given by a complicated formula, where r_s equals 2gm divided by c squared, where g is the gravitational constant, m is the mass of the object, and c is the speed of light. For our Sun, this radius would be about 3 kilometers. For Earth, it's roughly 9 millimeters, about the size of a marble. Don't worry, neither the Sun nor Earth is in any danger of spontaneous collapse into a black hole. The Sun isn't massive enough to end its life as a black hole, and Earth, well, let's just say we have other things to worry about first. What's crucial to understand is that once matter crosses this boundary, classical physics tells us it's doomed to fall toward the center, or singularity, where density becomes infinite, and our equations break down completely. This is where things get interesting from a gateway perspective. What happens at the singularity? Types of black holes and their properties. Not all black holes are created equal. We generally classify them into several types. Stellar mass black holes form when massive stars, typically those with initial masses greater than 20 to 25 solar masses, reach the end of their nuclear fuel supply. When nuclear fusion can no longer support the star against its own gravity, the core collapses catastrophically in what we call a supernova explosion. If the core remnant exceeds about 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, nothing can stop the gravitational collapse, and a black hole forms. Intermediate mass black holes are somewhat mysterious objects with masses between stellar and supermassive black holes. We have observational evidence for their existence, but their formation mechanisms remain unclear. Supermassive black holes are the giants, containing millions to billions of solar masses. These titans lurk at the centers of most galaxies, including our own Milky Way, where Sagittarius A times weighs in at about 4 million solar masses. How these monsters formed so early in cosmic history remains one of astronomy's great puzzles. Primordial black holes are purely theoretical objects that could have formed in the early universe from density fluctuations, without requiring stellar collapse. These could have a wide range of masses, potentially from microscopic scales up to stellar masses. Rotating black holes. The Kerr solution. Here's where things get more complex and more interesting for our gateway discussion. Most black holes in the universe are probably rotating. After all, the stars that formed them were rotating. In 1963, Roy Kerr found the solution to Einstein's equations for a rotating black hole, called the Kerr metric. Rotating black holes have some fascinating properties that non-rotating ones don't. They have two event horizons, an inner and an outer one. Between these horizons lies a region called the ergosphere, where space-time itself is dragged around by the rotation. More importantly for our discussion today, the mathematics of rotating black holes reveals some very strange possibilities about what might exist beyond the event horizon. Part 2. The mathematical foundations of gateway theories. Einstein-Rosen bridges, the original wormhole. Now we're getting to the good stuff. In 1935, Einstein and his colleague Nathan Rosen were exploring the implications of general relativity when they discovered something remarkable in the mathematics. They found that the Schwarzschild solution, when extended maximally, doesn't just describe a black hole, it describes a bridge connecting two separate regions of spacetime. Picture a flat sheet of paper. This represents normal spacetime. Now imagine poking two holes in this sheet and connecting them with a tube. This tube represents an Einstein-Rosen bridge, or what we now call a wormhole. Mathematically, this bridge connects the black hole in one universe to a white hole, the time reverse of a black hole, in another region of spacetime. A white hole is a theoretical object that's essentially a black hole running backward in time. Instead of everything falling in, everything emerges from it. The mathematics works perfectly, but we've never observed a white hole in nature, which raises important questions about whether these solutions represent physical reality or are merely mathematical curiosities. The problem with classical Einstein-Rosen bridges. Here's where classical physics throws us a curveball. While the mathematics allows for these bridges to exist, they're inherently unstable. Any attempt to traverse an Einstein-Rosen bridge would cause it to pinch off faster than light could travel through it. It's like trying to send a letter through a collapsing tunnel. The tunnel collapses before your message can get through. Moreover, these classical wormholes connect to regions of spacetime that are causally disconnected from our observable universe. You can't send signals or travel between the two mouths of such a wormhole. This makes them fascinating mathematically, but essentially useless as practical gateways. Traversable wormholes, the Thorne revolution. The game changed dramatically in the 1980 seconds when Kip Thorne, yes, the same Thorne, who later won a Nobel Prize for his work on gravitational waves, began seriously investigating whether stable, traversable wormholes could exist. Working with his graduate students, Thorne developed the mathematics for what became known as traversable wormholes. These theoretical constructs would allow not just information, but actual matter and energy to pass from one mouth of the wormhole to the other. But there's a catch, isn't there always? To keep a traversable wormhole stable requires something called exotic matter. This isn't exotic in the sense of rare and expensive, but exotic in the sense of violates the energy conditions that we believe govern normal matter. Exotic matter and negative energy density. Exotic matter must have negative energy density. Now, I can see some confused faces, so let me explain what this means. Normal matter and energy contribute positively to the curvature of spacetime. They create attractive gravitational fields. Exotic matter would do the opposite. It would create repulsive gravitational effects. The requirement for negative energy comes from the need to keep the wormhole throat open against its natural tendency to collapse. Think of it like trying to keep a balloon inflated, but instead of blowing air into it, you need to somehow create negative pressure that pushes outward from within. Quantum field theory tells us that negative energy density is possible, at least in small quantities and for short periods. The Casimir effect, for instance, involves negative energy density between closely spaced conducting plates. However, the amounts of negative energy required to stabilize a human traversable wormhole are enormous, far beyond anything we can produce or perhaps even conceive of producing with any foreseeable technology. The Morris-Thorne wormhole. In their seminal 1988 paper, Michael Morris and Kip Thorne provided the mathematical blueprint for a stable, traversable wormhole. The Morris-Thorne wormhole has several key features. 2 asymptotically flat regions connected by a throat. No event horizons. Travelers can go through and return. Finite travel time, as measured by the traveler. No singularities along the path through the wormhole. The metric for such a wormhole can be written as a complicated equation that has a bunch of letters, but is ds squared equals minus c squared dt squared plus dl squared plus r of l squared. Open parenthesis d theta squared plus sine squared theta d phi squared. Close parenthesis. Did you get all that? Good. Where L is a coordinate that goes from negative to positive infinity, passing through L equals 0 at the throat, and R of L is the radius of the wormhole as a function of L. The key insight is that R of L must have a minimum value R to the sub-zero at L equals 0, and the function R of L must satisfy certain conditions to ensure the wormhole remains traversable. Part 3. Quantum mechanics enters the picture. Hawking radiation and the information paradox. Just when we thought we had black holes figured out, Stephen Hawking dropped a bombshell in 1974. Using quantum field theory and curved spacetime, Hawking showed that black holes aren't perfectly black. They emit radiation due to quantum effects near the event horizon. Here's the simplified version. Quantum mechanics tells us that empty space isn't really empty. It's filled with virtual particle pairs that pop into existence and immediately annihilate each other. Near a black hole's event horizon, sometimes one particle from such a pair falls into the black hole while the other escapes. The escaped particle becomes real Hawking radiation, represented by the formula T sub h equals 8 pi g mk sub b h bar c cubed. And no, I won't repeat that. This discovery led to one of the most profound puzzles in modern physics, the black hole information paradox. If black holes evaporate completely through Hawking radiation, what happens to the information that fell into them? Quantum mechanics insists that information cannot be destroyed, but general relativity suggests it disappears when the black hole evaporates. The holographic principle and black hole interiors. The information paradox has led to revolutionary ideas about the nature of black holes and space-time itself. One of the most important developments is the holographic principle, which suggests that all the information contained within a volume of space can be encoded on its boundary. Applied to black holes, this means that everything that falls into a black hole might actually be encoded on its event horizon, like a hologram. From this perspective, the black hole interior might not be a separate region of space-time at all, but rather a holographic projection of information stored on the surface. This idea has profound implications for black holes as gateways. If the interior is holographic, then the question becomes, what is the hologram projecting, and where is it projecting to? Quantum error correction and black holes. Recent work has shown remarkable connections between quantum error correction, the foundation of quantum computing, and the structure of black holes. The idea is that the interior of a black hole might be constructed from quantum entanglement between degrees of freedom on the boundary. This suggests a radically different picture. Instead of black holes being gateways to other regions of spacetime, they might be gateways to entirely different representations of the same information, like looking at a three-dimensional object from different angles. Part 4. String theory and extra dimensions. The landscape of string theory. String theory, our most ambitious attempt at a unified theory of quantum gravity, provides another avenue for understanding black holes as gateways. In string theory, black holes are not points of infinite density, but extended objects made of strings and branes, higher dimensional surfaces. String theory requires extra spatial dimensions beyond the three we experience. These extra dimensions might be compactified, curled up so small we don't notice them, or they might be large but accessible only through gravitational effects. Black holes as branes. In some string theory scenarios, black holes can be understood as configurations of branes in higher dimensional space. A black hole in our three-dimensional space might actually be the cross-section of a much larger object in higher dimensions. This perspective suggests that what we perceive as falling into a black hole might actually be movement along these extra dimensions. Instead of being crushed at a singularity, matter might be transported to different regions of the higher dimensional space. The ADS divided by CFT correspondence. One of the most important discoveries in theoretical physics over the past 25 years is the ADS divided by CFT correspondence, discovered by Juan Maldacena in 1997. This correspondence shows that a theory of gravity in a higher dimensional space, ADS space, is mathematically equivalent to a quantum field theory without gravity on the boundary of that space. Applied to black holes, this correspondence suggests that the physics inside a black hole in the higher dimensional space is completely encoded in quantum field theory on the boundary. This provides another sense in which black holes might be gateways, not to other regions of physical space, but to entirely different mathematical descriptions of the same physical reality. Part 5. Modern Theoretical Developments. ER equals EPR. The Maldacena-Susskind conjecture. In 2013, Juan Maldacena and Leonard Susskind proposed one of the most audacious ideas in modern physics, that Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen entanglement, quantum entanglement, are the same phenomenon. Their conjecture, known as ER equals EPR, suggests that whenever two systems are quantum entangled, they're connected by a wormhole. This would mean that quantum entanglement, which we observe routinely in laboratory experiments, is actually a form of geometric connection through spacetime. If this conjecture is correct, then black holes, which create maximal entanglement between their interiors and exteriors, would necessarily be connected to other regions of spacetime by wormholes. Every black hole would be a gateway, not by design, but by the fundamental nature of quantum entanglement, the black hole firewall paradox. The plot thickened further in 2012 when Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, collectively known as AMPSI, presented the firewall paradox. They argued that maintaining the consistency of quantum mechanics requires that black hole event horizons be surrounded by a firewall of high-energy particles that would incinerate anything attempting to cross. This creates a paradox because general relativity predicts that someone falling into a large black hole should experience nothing special when crossing the event horizon, a principle known as the equivalence principle. The firewall paradox has sparked intense debate about the fundamental nature of black holes in spacetime. Some proposed solutions to the firewall paradox involve modifying our understanding of black hole interiors in ways that could support gateway theories. For instance, if the interior is somehow non-local or connected to other regions through quantum entanglement, the paradox might be resolved. Wormholes and quantum teleportation. Recent theoretical work has shown surprising connections between traversable wormholes and quantum teleportation protocols. In 2017, Ping Gao, Daniel Jafferis, and Aaron Wall showed that a specific type of quantum teleportation protocol in the boundary theory corresponds to traversable wormhole travel in the bulk spacetime according to ADS divided by CFT correspondence. This work suggests that the physics of traversable wormholes is intimately connected to quantum information protocols that we can actually implement in laboratories. While we can't build macroscopic wormholes, we might be able to study their physics through quantum teleportation experiments. The The holographic principle revisited. The holographic principle has evolved significantly since its inception. Modern formulations suggest that the information content of any region of space can be encoded on its boundary, but the encoding might be much more complex than originally thought. For black holes, this might mean that the interior isn't simply a holographic projection of the boundary, but rather that both interior and boundary are different projections of some more fundamental underlying reality. This could provide a sense in which black holes are gateways, not to other places, but to other ways of understanding the same underlying physics. Part 6. Observational considerations and constraints. What would we see? Let's take a step back from pure theory and ask, if black holes really are gateways of some kind, what would we observe? This is crucial because extraordinary claims require extraordinary evidence, and gateway theories certainly qualify as extraordinary. First, let's consider what we currently observe about black holes. We've detected them through their gravitational effects on nearby matter, through the gravitational waves they produce when they merge, and through direct imaging of their event horizons, as achieved by the Event Horizon Telescope for M87 times and Sagittarius A*. If black holes were functioning as active gateways with matter or energy regularly passing through them, we might expect to see several observational signatures. Energy conservation violations. If matter disappears into a black hole gateway and emerges elsewhere, we might observe apparent violations of energy conservation in the local region around the black hole. Unusual Hawking radiation. The spectrum and intensity of Hawking radiation might differ from theoretical predictions if black holes have internal structure more complex than classical general relativity predicts. Information flow. We might detect information-bearing signals emerging from black holes, violating the classical prediction that information cannot escape. The Event Horizon Telescope results. The Event Horizon Telescope has provided our first direct images of black hole event horizons, showing the shadow of the supermassive black holes in M87 and our own galaxy. These observations have been remarkably consistent with the predictions of general relativity. The images show the characteristic features we expect, a dark shadow surrounded by a bright ring of glowing matter. There are no obvious signs of matter or energy emerging from the event horizon in ways that would suggest gateway activity. However, it's important to note that these observations probe only the immediate vicinity of the event horizon. If gateway effects occur deep within the black hole interior, they might not be observable through electromagnetic radiation. Gravitational wave constraints. The detection of gravitational waves from merging black holes has opened a new window into black hole physics. These observations probe the strong field regime of gravity in unprecedented detail and have consistently confirmed the predictions of general relativity. When two black holes merge, they produce gravitational waves with specific characteristics determined by their masses and spins. If black holes had significant internal structure due to gateway physics, this might affect the gravitational wave signals in detectable ways. So far, all observed black hole mergers have produced gravitational waves consistent with the merger of objects described by the Kerr metric, rotating black holes as predicted by classical general relativity. This places constraints on how exotic the internal structure of black holes can be. Constraints from thermodynamics. Black hole thermodynamics provides another set of constraints on gateway theories. The laws of black hole thermodynamics, discovered by Jacob Bekenstein and Stephen Hawking, relate a black hole's entropy to the area of its event horizon, not its volume. This area law for entropy is one of the key pieces of evidence supporting the holographic principle. If black holes were classical gateways to other regions of space-time, we might expect their entropy to scale with their volume instead of their surface area. The fact that black hole entropy follows the area law suggests that whatever is happening inside black holes, it's fundamentally different from what we might naively expect for a classical gateway. Part 7. Alternative gateway scenarios. Black holes as gateways to baby universes. One of the most speculative but scientifically serious gateway scenarios involves the possibility that black holes give birth to new universes. This idea, developed by physicists like Lee Smolin and Alan Guth, suggests that the extreme conditions inside black holes might lead to the creation of new expanding regions of spacetime. In this scenario, what we perceive as the singularity at the center of a black hole might actually be the Big Bang of a new universe. The matter that falls into our black hole would provide the initial conditions for this new universe, which would be completely disconnected from our own except through the original black hole. This theory has several attractive features. It provides a natural mechanism for universe creation and might explain some observed properties of our own universe. If universes tend to produce black holes, and black holes tend to produce new universes, this could create a form of cosmic natural selection, where universes with properties that lead to more black hole formation become more common. However, this scenario faces significant challenges. The new universes would be completely inaccessible to us, making the theory difficult to test. Moreover, the mathematical details of how the transition from collapse to expansion would occur remain unclear. Quantum bounce scenarios, another class of gateway theories, involves the possibility that quantum effects prevent the formation of classical singularities inside black holes. Instead of crushing matter to infinite density, quantum gravity effects might cause a bounce that connects the black hole interior to other regions of spacetime. Loop quantum gravity, one of the main approaches to quantum gravity, predicts that quantum effects should become important at scales near the Planck length, about 10 circumflex, -35 meters. At these scales, the smooth geometry, assumed by classical general relativity, breaks down and is replaced by a discrete quantum structure. In some loop quantum gravity models, the collapse of matter in a black hole interior is halted by quantum effects, and the matter then re-expands, potentially emerging through a white hole in another region of spacetime or even in another universe. These quantum bounce scenarios are mathematically sophisticated, but they face the challenge that the quantum effects responsible for the bounce would occur at energy scales far beyond anything we can currently probe experimentally. Black holes as holographic gateways. Perhaps the most subtle form of gateway theory emerges from the holographic principle itself. If the physics inside a black hole is completely encoded on its event horizon, then in some sense, the black hole interior doesn't exist as an independent region of spacetime. Instead, the interior might be a holographic projection created by quantum entanglement between degrees of freedom on the event horizon. When matter falls into such a black hole, it doesn't travel to a separate interior region. Instead, it becomes part of the holographic encoding on the boundary. From this perspective, black holes are gateways not to other places, but to other representations of the same information. Falling into a black hole might be like entering a room of mirrors. You don't go anywhere new, but your perspective on reality becomes fundamentally altered. This holographic gateway scenario is consistent with our current understanding of quantum gravity and doesn't require exotic matter or violations of known physics. However, it's so conceptually radical that its implications are still being worked out by theorists. Part 8. Implications and future directions. Technological implications. Let's indulge in some speculation about the technological implications of gateway theories, while keeping our feet firmly planted in scientific reality. If any form of black hole gateway phenomenon were real and controllable, the implications would be staggering. Interstellar travel. The most obvious application would be transportation across cosmic distances. Current propulsion technologies would require tens of thousands of years to reach even the nearest stars. Traversable wormholes could, in principle, connect distant regions of space, making interstellar travel practical. Communication. Even if we couldn't send matter through black hole gateways, being able to send information would revolutionize our ability to explore and understand the universe. Instantaneous communication across galactic distances would be possible. Energy sources. Some gateway scenarios involve connections to regions with different physical properties. If we could tap into these connections, they might provide access to vast energy sources. However, we must emphasize that these applications require not only that some form of gateway physics exists, but also that we could control and harness it with technology. The energy scales involved in black hole physics are so enormous that any practical application seems far beyond our current technological capabilities. Experimental and observational programs. While we can't build black holes in laboratories, there are several ways we might test aspects of gateway theories. Analog systems. Researchers have created analog black holes using systems like flowing fluids, ultra-cold gases, and optical media. These systems can mimic some aspects of black hole physics and might help us understand quantum effects near event horizons. Quantum information experiments. The connections between wormholes and quantum entanglement suggest that we might be able to study aspects of gateway physics through quantum teleportation and other quantum information protocols. Advanced gravitational wave detectors. Future generations of gravitational wave detectors might be sensitive enough to detect subtle deviations from classical black hole physics that could indicate exotic internal structure. Space-based telescopes. Advanced space telescopes might be able to detect subtle effects of gateway physics, such as unexpected energy flows near black holes or deviations from expected thermodynamic behavior. Theoretical challenges. Gateway theories face several major theoretical challenges that must be addressed. The grandfather paradox. If wormholes connect different regions of space-time, they might allow closed time-like curves, paths through space-time that return to their starting point in the past. This raises causality paradoxes that are difficult to resolve. Exotic matter requirements. Most traversable wormhole scenarios require forms of matter or energy that violate known energy conditions. It's unclear whether such exotic matter can exist in the quantities required. Stability issues. Even if traversable wormholes can exist, maintaining their stability against perturbations is extremely challenging. Any realistic wormhole would likely be unstable against small disturbances. Quantum effects. The interplay between quantum mechanics and general relativity in the context of wormholes and black holes remains poorly understood. Quantum effects might either stabilize or destabilize potential gateway structures. The future of gateway research. Research into black hole gateway theories is likely to continue along several fronts. Advances in quantum gravity. Progress in developing a complete theory of quantum gravity, whether through string theory, loop quantum gravity, or other approaches, will be crucial for understanding what really happens inside black holes. Improved observations. Better telescopes and detectors will provide more detailed observations of black holes and their environments, potentially revealing signatures of exotic physics. Quantum simulation. Advances in quantum computing and simulation might allow us to model complex quantum systems that are analogs of black hole physics. Mathematical developments. Continued progress in understanding the mathematics of general relativity, quantum field theory, and their intersection will be essential for developing and testing gateway theories. Part 9. Philosophical implications. The nature of reality. Gateway theories raise profound questions about the nature of reality itself. If black holes are indeed gateways, whether to other regions of space-time, other universes, or other representations of information, what does this tell us about the fundamental structure of existence? The holographic principle suggests that the three-dimensional reality we experience might be a projection of information encoded on two-dimensional surfaces. Gateway theories push this idea further, suggesting that what we perceive as separate regions of space-time might actually be different aspects of a single, more fundamental reality. This has echoes of ancient philosophical questions about the relationship between appearance and reality. Are we seeing reality as it truly is, or are we observing shadows on the cave wall, as Plato suggested? Gateway theories suggest that even our most sophisticated physical theories might be describing only one perspective on a reality that is far richer and more interconnected than we imagine. The role of information. Modern physics increasingly suggests that information, rather than matter or energy, might be the most fundamental aspect of reality. Gateway theories take this idea to its logical conclusion, suggesting that black holes might be information processing systems of cosmic scope and complexity. If black holes are indeed gateways for information, this could mean that the universe itself is a vast information processing system, with black holes serving as nodes in a cosmic network. This perspective has implications for our understanding of consciousness, computation, and the relationship between mind and matter. The multiverse connection. Many gateway scenarios involve connections to other universes or regions of space-time that are causally disconnected from our observable universe. This connects gateway theories to multiverse theories and raises questions about the meaning of existence itself. If there are infinitely many universes connected by black hole gateways, what makes our particular universe special? Are we just one branch in an infinite tree of reality, connected to others through these cosmic portals? These questions push us to the boundaries of science and philosophy, where testable hypotheses become difficult to formulate, and the line between physics and metaphysics becomes blurred. Conclusion: the gateway to understanding. As we reach the end of our journey through the theoretical landscape of black hole gateways, let's take a moment to reflect on what we've learned and what it means for our understanding of the universe. We've seen that the mathematics of general relativity, from its very beginning, contained hints that black holes might be more than simple points of gravitational collapse. Einstein and Rosen's discovery of bridges in space-time, Kerr's rotating black hole solutions, and modern developments in quantum gravity all point toward the possibility that black holes are far stranger and more complex than they appear. The various gateway scenarios we've explored, from classical wormholes to holographic projections to quantum information networks, each offer different perspectives on how black holes might serve as connections to other realms of Cardan's existence. While none of these scenarios has been definitively proven, each is grounded in serious mathematical physics and addresses real puzzles in our current understanding. Perhaps the most important lesson is that black holes continue to be laboratories for testing our most fundamental ideas about space, time, matter, and information. They push our theories to their limits and reveal deep connections between seemingly disparate areas of physics. Whether or not black holes turn out to be literal gateways to other regions of space-time, they are certainly gateways to deeper understanding of the universe. They force us to confront the limitations of our current theories and point toward new physics that might revolutionize our understanding of reality itself. The story of black hole gateway theories also illustrates the power and beauty of theoretical physics. Through pure mathematical reasoning, guided by physical intuition, and constrained by experimental observations, we can explore possibilities that stretch the imagination and push the boundaries of human knowledge. As we continue to develop more powerful telescopes, more sensitive detectors, and more sophisticated theories, we will undoubtedly learn more about these cosmic enigmas. Whether black holes turn out to be gateways, holographic projections, information processors, or something else entirely, one thing is certain: they will continue to surprise us and challenge our understanding of the cosmos. In closing, let me leave you with this thought. We live in a universe where the collapse of massive stars can create regions of space-time so extreme that our best theories break down, and our imagination is challenged to keep up with the mathematics. Whether these regions serve as gateways to other realms or represent the limits of physical reality, they remind us that the universe is far stranger, more beautiful, and more interconnected than our ancestors ever dreamed. The next time you look up at the night sky, remember that scattered throughout the cosmos are these invisible monsters and potential gateways, warping space-time around themselves, and possibly connecting our universe to realms beyond our current comprehension. In studying them, we're not just learning about distant astronomical objects. We're exploring the deepest foundations of existence itself. And who knows? Maybe someday, one of you will make the discovery that finally reveals whether black holes are truly gateways to the unknown, or something even more extraordinary that we haven't yet imagined. Thank you for joining me on this journey to the edge of known physics and beyond. For next class, please read on gravitational waves, and remember, extra credit goes to anyone who can solve the traversable wormhole stability problem. I'm only half joking about that. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you.